will mainly be like group theory, not exactly group theory talk series, it's representation of groups. So we basically will be dealing with two mathematical objects or structures. One is group, another is vector spaces. So I'll start by talking about groups with very basic definitions and all these things, and then I'll go to vector space. We'll complete those two, and then we'll define the representation, how linear representations are defined, and then some of the examples of groups as well as the vector spaces. And then we'll first start with, let's say, some properties of finite groups, and with a more like kind of general definitions, so that those can be applied to infinite groups or the topological groups or Lie groups as we say. And then we'll go to some like applications of these linear representations, which basically mainly quantum physics, because quantum physics has inbuilt structure of vector spaces. We often say that quantum physics lives in Hilbert spaces, so it's basically vector space plus some additional structures. So there, and the symmetry will be represented by some transformation symmetry, and those will form a group, and we'll see the connection between these linear representations of groups on a like vector space in that context. So that will be our final goal. But before that, we will go a bit mathematical approach. So basically, we will not talk about much physics as of now. First few lectures we'll try to develop the mathematical foundations of linear representations, groups, and vector spaces, and then we'll go on to apply those things in physical systems, especially in quantum mechanical systems, quantum physical systems. Okay, so generally we don't go into much, physics students don't go into much details of mathematical structures and all, but I will encourage you to do so, or think about at least some basic foundations of mathematical. What does it mean by set and functions and all these things, so that anytime you come like get some group, or let's say somebody tells you that this is a representation, irreducible representation, and all this jargon, you immediately know that what is going on inside it, and then if you want to try to find out what is going on, you can find out. So that's the basic like motivation of this series. Okay, so first let us say, so this will be a bit mathematical. So I want you to interact as soon as you encounter a problem, and we will discuss it further and try to give let's say some examples if that helps or something. But please try to stop me at any point you don't understand, so that you can actually understand it better. Okay, so first in mathematics we always start from a set. Okay, so set. So we'll not go into very deep about sets and its axioms and all these things, but some basic things we already know. We just start from there so that we can build upon the sets and then go to some complicated structure in mathematics. Okay. So first, and we'll of course follow a very specific path, like group, vector spaces, and then representation. But it's not a full course on representation theory, so we'll choose a specific path that will help us in general in high-energy physics. More of. Okay, so let us start by, let's say, a set. It's a mathematical object we know. Set by definition is a collection. What is a set? Set is a collection. Actually, sometimes we call it well-defined collection of objects. So we generally have notion of set, and we denote a set by capital letter, and generally it contains or its object, whatever the collection, are written in curly braces, and there are some other notations also. Usually what we do is we say, let's say, we define a set by their property, some property is specified, and whoever satisfies those properties are the elements of set. And let's say if A is an element of set A, capital A, then we usually write it in terms of in this notation. And if A is not an element of set A, we write it in this fashion. So this is a familiar structure. And if there are two sets, let's say A and B, we often call A union B is the set of all the objects, okay, A, such that A either belongs to capital A or belongs to capital B. So it's basically, in the Venn diagram we represent it in terms of, let's say, if this is set A, okay, this is the representation of the set A and set B, then this whole thing is basically A union B, and A intersection B is represented by, or A intersection B is defined as the set of all elements such that the element belongs to set A as well as set B. So it comes from both the sets. So A such that A belongs to A and A belongs to B, both the sets. So that is basically this area that we usually see. Okay, so let us now move on to the second let's say part we call let's say Cartesian product. Okay, so now let's say we have a set A. So there are other various properties of sets and other things, the modern property that we not tell here. If we need it, we tell it at that point. Okay. So now we go to another, let's say, important concept in mathematics. It's called function, or sometimes they call it mapping. What is a function or a mapping? So in general, it's usually in physics when we see function, we have some expression or some graph or something like that. But in mathematics, what function is basically a rule of assignment. How the assignment is done. Let's say you have a set A and set B. Okay. So a rule of assignment is basically that you have assigned every element of set A. Okay. Let's say if small a is an element of set A, capital A, okay, we'll assign this to some element of B. Okay. So let's say now they may not be the same type of set. So let's say you have set A and set B here. Okay. So for each element in A, you assign one element, exactly one element, not more than one element. Okay. Exactly one element in B, and that is your rule of assignment. So for every element in capital A, you assign exactly one element in B. So let's say this is A1, you assign an element B1 here, another element B2 here, let's say for A2, A3, you may assign the same element in B. But so what is the condition? For every element you have to assign one element of B. And for every element, each element exactly one element here. Okay. But it's not necessary that two elements cannot have cannot point to single object here. Okay, so that's the definition. So you may point this A3 to B2 as well. So that's allowed. But what is not allowed is A3 points to B2 as well as point B3. This is not allowed. Okay. So one element will point to one element here, but two elements can point to the same element here. Okay. So that's the rule of assignment, and every element has to be assigned to this. There may be some extra element in B, okay, which you may not assign some variable from here to there. That's perfectly allowed. But here, whatever element you have to assign some variable, some object to B. So that's the rule we say, and they are usually represented by f. So we usually represent, if this type of rule of assignment we give, we usually call it as a function or map. So if, let's say f is a rule of assignment, then we call it f a to b. So this is the notation.
most generic definition of function.
Yeah, this is the definition of function.
But
Not
what's
the
the
mapping, right? Mapping is more general, right? Mapping is more general, right?
Function or mapping is same in mathematics.
But say some square root takes.
Mhm.
We can take it a function.
No,
If-
in mathematical sense, square root, like,
Square
root of
root.
x is plus minus square root.
So what you are trying to say, let's say, so let's go more concrete way. So you are saying that I want square root of a real number, right? So it's real number, and at the end we'll get what? Another real number. Okay? So
Positive
this is
real
the
number.
mapping.
Positive real number.
Mhm.
The first set is the
But
positive.
yes. So but usually square root is always defined, if you don't say it anything, it's always defined as the positive real number only. So you can have the more wider range here, that's not a problem. But if of x is always assigned to square root of x, let's say, if it is a square root function, and this always comes with plus sign. Okay. So a function by definition cannot have two outputs. It's always one output. So that's the thing. And yes, and by if f is a mapping from A to B, A is called its domain and B is called codomain. And if you take the image, all the collection of all the images of the elements of A, so then it's usually notation wise it's written as f of A. It does not, it's like some like abuse of notation we'd say, but it's perfectly defined in mathematics. Okay, so f of A is basically collection of all the if A such that A belongs to. That means you take all the elements, okay, of A, take its image, okay, and take that collection. It will be that will be called as f of capital. Okay. So it's basically a subset, and by definition, it is actually a subset of. By the way, the subset notation is this. Notation is this, and another like notation that we may use. I don't know whether we'll be using it. So this is one thing, and if f is a function, or if A, this thing is called the range of. Is this definition correct? Range of. Okay, and okay. So if f is a mapping from A, we call A into B. Okay. Sometimes what we say, if A is an element, small a is an element of capital A, we sometimes write this way as if. So we say f points to f of A in B. Okay. So this is in set to set. This is element of a set to element of the other set, the codomain set. So by the way, I am now confused about range and codomain. Is that correct, right? Whatever I say.
I'm not sure. I was confused.
One is called codomain. Okay, fine. So this is another notation thing. Okay. And what else in function? What else in function? Okay. So now, so this is one thing, and as we say that this one to many is not allowed, but many to one is allowed in the definition of functions or mapping. Okay, so now if for all the elements in A, it points to exactly one element and there is no many to one, then we call it one-to-one mapping. One-to-one. Okay. We call it one-to-one or injective. Okay. And another thing that we saw that it is not necessary that all the elements of B have to have B images in A. Okay, it's not necessary. Okay, but if it is the case that all the elements in B have B images in A, then we call it a onto mapping, onto or surjective. Okay, so one-to-one is every element is pointing to one element, but so B, if B some B belongs to B, it does not have two pre-images, two or more than two pre-images, then we call it one-to-one. So one element points to one element and that element does not point back to some other element. And if these two conditions are satisfied together, then we call it one-to-one and onto, or one-to-one and onto, or we call it bijective. So bijective is when every element of A, so elements of A, capital A, points exactly one element here. That is the necessity condition for the function. But this is one-to-one mapping, and every element of B has a B image in A. Then we call it a bijective mapping. And in the bijective mapping, what we can have is basically we can define an inverse here. Because then, if we take the pre-image as the image of B or some other function, that will be our that is another function that we can define from B to A, because we have both the conditions satisfied for the rule of assignment for a function. Okay, so that's the function mapping. Then we'll go to, let's say, another important concept is Cartesian product. Okay, so let us say A is a set, B is a set. The Cartesian product A cross B is defined as the set of all ordered pairs AB such that A belongs to A and B belongs to B. This I think everybody is familiar with. So Cartesian product, you take all the elements from A and write for each element of B from capital B, you write AB, where exactly the first element comes from A, the second element in the ordered pair comes from B. And you take all the possible pairs, then it's the Cartesian product of A. Let's say, for example, if we have let's say A is 1, 2 and B is A, B, okay? Then the Cartesian product of AB will have 4 elements here. So first we'll take, let's say, 1 from capital A and pair it with 1 element from B, and then all possible pairs we have to consider, then 2A, 2B. Okay. So if A and B both are finite and it has n elements, it has m elements, then Cartesian product will have n times m or m times n elements. This is also kind of understandable. And important, interesting thing is we can always take Cartesian product with itself. Okay, so if A is a set, we can take A cross A as a Cartesian product. It will be another set. Okay. We can take furthermore, but we'll not go to that details now. So we can always take A cross A, B cross B as well. And now one interesting now Cartesian product and the mapping we'll combine. Let us say we can define, let's say we can define, okay, a mapping from A cross A. Okay. This is a set to A itself. Let us say we have a mapping. What does it tell me? It tells me you give me two numbers from the set. I'll give you another number. You give me two numbers from a single set. Okay? Same set. I'll give you another number. This type of structure we all have already seen. You give me two real numbers, let's say 2, 3, and 2. I'll say, okay, I'll multiply this and give you another real number. You give me 2.5 times, let's say 4.5, I'll give you another real number. Right? So it's exactly the multiplication, the operation multiplication we define can be thought of as a mapping from R cross R to R itself, or maybe from integer set times integer set to the integer set itself. And these type of mappings are called, addition operation can also be thought of as the mapping from A cross A, Cartesian product, to A, right? In real number set, or in rational number set, or in integer. Okay. So this type of mapping, if this type of mapping is possible, okay, then we call it as a binary operation. The name, we clearly understand why this is binary operation, because we take two same type of object and operate it binary, and then we get a same type of object here. Okay. So familiar examples are, let's say, for example, multiplication. This is the symbol of multiplication, and Cartesian product symbol are same. Okay, multiplication of, let's say, real number times real number, Cartesian product to real number, is a binary operation. Let us say addition, okay, real number is, will get another real number. This is also a binary operation. Okay, so binary operation can be thought of as a mapping from the Cartesian product of, let's say, same set, between same sets to the same set itself. So this is how the binary operation is kind of defined. Okay. Now let us come to the definition of group now by this object, this structure. So now we may call that this, once this one type of binary operation, you don't need to give the same binary operation. You can have different types of binary operation. You can define your own binary operations in the set. But the requirement is for every ordered pair in the set, I mean, give two real number, you have to give me another real number. That rule you have to define. But it not necessarily that multiplication, usual multiplication or usual addition. It can be some other things also that you yourself can define. Okay. So in that way, you can actually define the binary operation. Now let us say a set G is equipped with a binary operation. Let's say start. This is equipped with a binary operation. Somehow I managed to give some binary operation. That means you give me two elements from this set. Okay, I'll give you another element from this set. Okay, is equipped with a binary operation with the following property. With the following first, let's say G1 times G2 I take, so once this is defined, we can always define, we can take another Cartesian product, because first we can multiply, let's say, act this binary operation on two objects from this set. I'll get another object and take that object and take another object from the same set. I'll get another object from the set. I mean, the output will be another object from the same set. So that way, let's say G1, G2 are objects from set A, G, and then I get some output, and then I act another binary operation with G3 from G. And if it is equal to G1 times G2 times G. So this is called associativity. Second is existence of inverse. Let's say there exists an element, let's say call it E, such that G times E is equal to E times G is equal to G. Okay. For all, so by the way, there is a notation for all G belongs to capital G. And for all G belongs to capital G, there exists G inverse such that G times G inverse is equal to G inverse times G is equal to identity. Okay. So if I have a set equipped with binary operation, and the binary operation is such that it satisfies all these three properties, then G will be called a group, and the group multiplication is this binary operation. Okay. Any question? So group. Okay. Sometimes we, in general in physics, since we do not approach group definition via binary operations, we usually call another property here, we say the closure property. Okay. But the closure property is what? That you give me two elements, I'll get another element from the same set. So that is inbuilt in the binary operation. Okay. Since we approach in this binary operation way, we can skip that as an assumption because it is inbuilt in this operation itself. So
Okay, now E is unique,
yes, E is unique.
and for a given G, G inverse is
G
unique.
inverse is unique. So G inverse is just a name. You can call it H, for example.
Whatever, that is unique, right?
Given H, yeah. So yeah. So now it's a simple exercise by which you can show that you cannot have two identities in a group. So that is, if you found, let's say, another identity, that must be equal to the first identity that you found. And for a given G, its inverse is also unique. Okay. You cannot have two inverses. Okay. So this is the definition of group. Let us see some examples of groups. Okay. So whenever you talk about group, you first have to find out what is the binary operation. Okay. So it's much more general. In general, we call multiplication or something, but sometimes it gives us little difficulty when we call, let's say, it's under composition, this is a group, or under addition, this is a group, or under subtraction, it is a group. Then we say, where is the multiplication? But in terms of binary operation, it's very clear. You don't have to think it as a multiplication. It's just binary operation. You give two objects from the two elements from the group. I'll give you another element from the group, from the same set. Then we call it a binary operation, and then if it satisfies all this associativity, existence of identity, and existence of inverse, then we call it a group. So kind of, this is a further structure. One structure is binary operation, and with all these properties, we basically give some structure to the set. It's not only some elements, a collection of some elements or some objects. And what is the interdependence of these elements inside a set that we are actually talking about here. So it's kind of like giving some structure. This is some rudimentary structure that we are giving to a set. Let's say, let's take some example of, let us say Z, Z is collection of all the integers, positive and negative. Okay. And we can naturally define addition here. We know if we add two integers, we'll get another integer, right? So addition is a binary operation from Z cross Z to Z. So this binary operation we already have. Okay. And with this user addition, let us check if these properties are satisfied or not. Property 1 says that if we take two numbers first, add the third, and we take second and third, add the first, will that be same? The answer is yes. So property 1 is checked. Okay. Second, is there any object, any element in this Z such that after addition with that element will get the first element itself? The answer is actually yes, because element 0 plays that role. Why? Because any integer, let's say I, plus 0 is equal to 0 plus I is equal to I. So 0 plays that role of identity. Third is existence of inverse. So since we have already taken positive and negative both the integers, so we know for every integer we have a minus of that, and that plays the role of the inverse. So let us say I have positive integer, let's say I, then if we add minus I to that, then it is exactly 0. Okay? So the minus I actually plays the role of inverse of the positive integers itself. So we can say that the collection of all the integers, positive and negative and 0, is a group under the binary operation addition. Okay. So Z, comma, plus is actually a group.
In the definition of group, like G1 star G2 is equal to G2 star G1. Is that there or
No, it's not there.
that is only for the inverse element?
That is only for the inverse element. That's for the inverse element. If that is the case, then it's called abelian group or commutative group. If A plus B, so yeah, here we can say that this is a commutative group because A plus B and B plus A actually gives us the same number. So A plus B is equal to B plus A. So this is not only a group, but this is a abelian or commutative commutative.
Can you give an example which is not abelian?
Oh, there are plenty of examples.
Just one.
Matrix multiplication. Okay, so this is a very simple example. Then one can check that, let's say, so this can be checked, for example, a group rational number Q, of rational numbers. Okay. Q under operation plus is a group. Okay. But Q minus our usual multiplication also forms a group. Okay. That can be said. Here, this is kind of obvious, okay, because multiplication and addition in rational number, integers, and even in real numbers, they are commutative and associative, that we know. What will be the what is this identity for this group? 0 is the identity and minus q is the inverse. Minus q is the inverse. But for this 1 is the identity, and since we have excluded 0 from it, so we have inverse for every element. It's if p by q is the rational number, then its inverse is q over p. Similarly, one can check that collection of real numbers, okay, and finally a function positive, and real number minus 0 and multiplication also a group, and all of them are actually commutative groups. Okay, and now let's say these are simple groups, and then let us come to the thing that I just talked about is, let's say, example C is, let's say, M is collection of all n cross n invertible matrices. All collection of all n cross n invertible matrices. Okay. So then we can say that this forms a group under usual matrix multiplication. So as we know that usual matrix multiplication for n cross n is a binary operation, because if I take, let's say, M1 and M2 to be two matrices, both are n cross n, then we under usual matrix multiplication we can multiply them and we'll get another M3, which is another n cross n matrix. So this is usual binary multiplication, and this is a binary operation. So that condition is checked. Condition 1 is checked as associativity, that we have already done. I will not go it further. So we know this is associative. This is checked, and then let's say third is this identity. Okay, so here also we know I n cross n identity matrix of order n plays the role of identity, because if we multiply identity matrix with any matrix, we'll get. And now comes the point where we need the invertibility of the matrix. Okay, so now we know that since we have already specified it is invertible matrix, so inverse of the matrix plays the role of the inverse under this binary operation. So that is also checked. Okay, and as Abhi was asking, that this is a binary operation where it is not commutative. Another interesting example could be okay, we did not discuss about composition of functions earlier. Now we will discuss the composition of functions. Okay. So let us say we have a set A, okay, another set B, another set C. Let's say there are three sets. We define one function from A to, okay. So that means you give me an element from A, I will say what it goes to in B. Okay. So I given an element A, I can say where it goes to in B. That rule I have already specified. Let's say we have another function from B to C. Any function. That's not this. So once So by this, what we can say that you give me one element from capital B, I'll say where it goes to. So basically, B goes to G of B. Can we naturally define a function from A to C directly? The question is, can we naturally define kind of natural from these two, induced by these two, can we define some function? The answer to this question, let's say 8. The answer is actually yes. First, we already have a rule, okay, of assignment from A to B, and then wherever it goes to, we'll take the second function from here, okay, and apply this function to this element. So this h is h we can naturally define to be the composition of. So what it will take, G compose H. What it will take is H. So what it will do is H of A. What I'll do, I'll take A. First, I'll send it to the set B via the rule F, and then whatever I'll get, I'll send it to C via G. So pictorially, we can say that okay, I have a set A here, I have a set B here, and I have a set C here. Okay. So any element I'll take here via F. Whatever I'll get, I'll impose the rule G on this, and whatever I will get, this rule, okay, this. So for every element, I'll get one element in the C, one rule. So that for the function, what we need to satisfy are two conditions. One is for every element of A, I have to specify a rule. Okay, and every element of A cannot point to two different objects in the next set. So these two conditions are satisfied via this composition. Because if I take A, it cannot point to two objects here, so it will exactly point to one object here, and that will point to exactly one object here. So by this translation, what we can see, if we take one object, it cannot point to two objects in C. And second is, any element I take, I can always go to B, and since G is also defined in that, in the same fashion, that every element in B should go to some element in C via the rule G. So whatever element I get, I can always send it to C via rule G. Okay. So H, which is then called as G compose F, is naturally defined from these two rules, two functions. So whenever I have set A to B, B to C, okay, we can always have a rule H which is called G compose F. And what it will do is basically it will send A to G of F of G. Right? That's fine. Now let us say, so this point, up to this point is fine, composition. Let us say I have a, let's say for this purpose, for example, let's take A is a finite group. Sorry, not a group, finite set of n elements, small elements. Now, I can always get a function from A to A. There are many functions, and let us say this A is bijective. How can I get that? We'll just permute the numbers or permute the elements of the set, then it will be a bijection. Okay, so basically what I am saying is, let's say A, for example, A has three elements, A, B, C. Okay, now F is what? F is a function. That means I have to define a rule. I have to say a rule from A to A itself, and such that it is a bijection. Bijection means it cannot point, it is not a many to one mapping, and it is not a into mapping, it's onto mapping. Let us say I permute this number. So under if A goes to, let's say, B goes to C goes to A. This is a bijection mapping, if that we can do. And there can be many more such bijection mapping. What I can do, another example would be, I same this object to itself. If B, if C, so there are many bijective mappings, not many, there are finite number of them. So it's basically, it can be obtained by permuting these elements of the set. So it's basically, there are, if there is a set with n elements, there are n factorial of the function which are bijective mapping from A to A itself. Let us now let us take a set denoted by Sn, okay, such that its collection of all the bijective mappings is such that if is a mapping from A to A and A is a bijection. So what we do, we have a set of n elements, okay, then whatever bijection mapping we can consider, okay, or collection of all such bijections, we will take it inside a set. Let us say it as Sn. Okay. This up to this is understood? Everyone is with me? Okay. This is fine. So then let us say if F1, let us say if F1 is from Sn. So this is, what is this? This is a bijection from A to A. Okay? And let us say F2 is another bijection. Can we say that F1 compose F2 is a bijection? Of course, F1, so F1 is a mapping from A to A, right? F2 is also another mapping, can be same, can be different, from A to A. Both are bijections. What about, let's say, F1 compose F2? Is it bijection? So this is clear, right? F1 compose F2 is a mapping from A to A. That part is clear. That we already discussed, A to B, B to C. So this is a mapping from A to A. That part is clear. Now whether we can call it a bijection mapping or not. Bijection or not, or bijective mapping or not. I don't know, maybe yes.
Yeah, yes, it is.
Yeah. Okay, so you may check it at your home. It's actually a bijection. So F1, F2 is also a bijection. Now you can take the full stop instead of question mark. And if that is so, then we can say that F1 composed F2, okay, also belongs to Sn, the set of the collection of all. So now we can naturally define a binary operation for the composition of function from Sn cross Sn to Sn. So if we take two functions from Sn, under this composition, it will be another function from the Sn itself. Right? So this is the composition operator, and just like the group, so we have a naturally binary operation, natural binary operation in the Sn itself. Okay? Now we have to check whether this is satisfied or not, associated. So you may actually check it, and it is much more general than the bijection mapping. For any mapping from A to A and then another mapping from A to A and third mapping from A to A, you can always check that this is always associated. Okay. It's not particular property of bijection, it's for any mapping. Okay. From A to A, then A to A, then A to A, it's always associated. So this condition you can check by yourself. And then, is there any mapping with which any composition will be the same mapping here? The answer is actually yes. We have one mapping which sends A to A itself, B to B itself, C to C itself. So under composition, if we take another G with this composition, since this is not changing, okay, so G will send A to A, G of A as usual. So this will play the role of the identity mapping. Identity mapping means which sends A to A itself, all the elements to itself, every element to itself. And is there any kind of inverse? The answer is yes, because by the definition of bijection, we always know that we can always have an inverse. The function which sends the image to its pre-image. Okay? So that's why we chose this bijection matching, so that the existence of inverse is guaranteed. Okay, so under this operation, Sn is a group. So Sn is a group. Sn is a group on its own right via the binary operation composition. And this group is called actually the symmetric group of symmetric or permutation of n. Okay, so there are many properties of symmetric group of n numbers and all these things, but we will not go to the details of it.
For the property one, how can we understand it? Like G1 of G2, then G3 of G of G2? Or for the property 1?
Property 1. So
Let's
that
say G1,
that is a general property. It's not specific to bijection. It's for any general property. Let us check. Let us say F1, F2, F3 are key functions from A into. Remember, we did not consider envelope here, so we don't need to consider. So what we know is, let's say, let A is an element of capital A. Okay. Let us now consider the action of F1, F2, composition of F3. Okay. On this element A. And for every element, we have to consider this thing. Let us take one, let's say, out of the all the elements. So this is F1 composed F2, okay, and then this is nothing but F of 3. Right? first F3 will act on this and give me F3 of right? Then what we'll do, so let us say A, like 3 copies of A, actually 4 copies we need. A, so actually we took it in the reverse order. So first we have to add F3. So F3, I have a mapping F2, another mapping F1. So we take an element A from here, and it will send somewhere here. F3, let's say this is F3. Then we'll take the rule F1 compose F2. So F1 compose F2. Yes. F1 compose F2 will directly send some element from here to here, since we have taken the whole thing together. But what is that? That is nothing but F2 first act on F1 compose F2 is already defined to be F1, then F2, then whatever the element I have. Yeah. And that element is nothing but F3. F1 compose F2 is defined that way. So it's basically F1, F2, F3. Now if you take the other way around, F1, then F2 compose F3, and then P. This is now trivial. You know, this is defined, this is essentially defined to be F2, F3. This is the definition. Okay, and then F1 is basically act on this. And then two are the same. It's basically just thinking wise it's like a little bit difficult, but if you put the definitions in, you will get the result directly. So this is another thing. This is the symmetric group of n objects. That's great. So let us give. Okay, so we have kind of enough examples here, and generally, in the case of discrete groups, so discrete group is which are not continuous, and there are like finite number of objects. We call it a discrete group. And generally, when we have a discrete group, we can have a multiplication of the objects. Let us consider S2. So, and what is the cardinality, or how many numbers of elements are there in Sn? Any idea? I mean, how many bijections you can consider from set A to A if A has n numbers, n elements? It's basically how many permutations you can do. It's n factor. So if we consider S2, for example, it will precisely have two elements. Okay? Let us call them F1, F2. So S2 is basically, let's say, if I have a group, if I have a simple set with two elements, A, B, okay? So there will be two functions which are bijections, not more than two, not less than two, which will form this group. Okay? So F1, let's say F1 is defined So if F1 is what? F1 is a function from A to E. Right. So f of, let's say F1 I define in this way, is basically identity net. And another permutation that we can do, only one more permutation we can do is F1A, sorry, if another, let's say bijection, F2A, it sends A to B, and F2B, so it's just permute A and B. And there is no more bijections you can consider independent of these two. Okay, so one permutation is you can send A to A, B to B, identity map, and another is A to B and B to A. Okay. So now let us check what are the all possible multiplications or under this composition, all the possible binary operations under this. So for any two elements from S2, I have to have a rule binary under the binary operation. Okay. So F1 compose F1, I need to say what it is. And that is very trivial, is basically the same F1. Why? Because if F1 sends A to A and then again F1 sends A to A, it will send A to A and B to B, etc. So F1 compose F1 is basically F1. F1 compose F2, but it is F2. It's F2 because F1 actually does not do anything on the side. F2 compose F1 is essentially F2, and F2 compose F2 is what? It's an A to B, B to A again, back, A to B to A to B, back. So it's nothing but A. And now we can clearly identify F1 plays the role of identity, and inverse of F1 is F1 itself, inverse of F2 is F2 itself. And in general, in the discrete group, what we usually write is, now let's get rid of all these properties of group or this thing. So what we can say is that for any two elements, I have to have a third element under the binary operation. So we can write that in terms of a table. So let's F1, F2 here, and two elements here, F1, F2. For any group we can write, and we usually write the operation, binary operation here. Okay, so in this case it's a composition. So now we have to clear about in which way we are doing the operation, since it's not always commutative. So let us say we write the element here such that this multiplied with this and this multiplied by this. So F1 is F1, F2, F1 compose F2 is F2, F2 compose F1 is F2, and F2 compose F1 is F1. Okay. So for any group, what we can do is basically create a multiplication table. If it is a discrete group, we can see it. If it is not a discrete group, it's not a discrete group, then it's difficult to see. But for the discrete group, we can always, if we have 3 elements, 4 elements, we have 4 elements, and we can kind of create a chart where we can say that this is my multiplication table under this binary operation. Okay. So that we can always do. We can do the same for, let's say, if A has 3 elements. Okay. Then actually we can, here we can consider F3, F4, F5 and F6. Total 6 number of elements here. Then this group, the table will be bigger. Okay. But we can always do that for the S3 case. Another important group is, so this is called SN group. Another important, not important but usually consider are called ZN group. So what is ZN group? ZN group is collection of one or power n minus 1 such that am yes p n q such that an is identity. This by itself forms a group. Okay. This collection of E to A to the power A is some object. It's not. We don't have to consider it to be some specific type of object. But let's say A is some object, and by A to the power n we mean A times A times A times A times A, and A to the power n is identity. Then it's a group. Let's say first property, whether this is associative. It's basically associative because it's basically we don't order. It's same A acting one, so we don't have a really order thing here. So associativity is assumed. Second, identity. Identity is E is the identity because if you multiply any A to the power R times this identity, it's essentially E times A to the power R times A to the power R, where R is less than. And what is the inverse? Inverse is A to the power n minus R will be your inverse. So A to the power R is A to the power n minus R is your basically A to the power n is identity. This will be the inverse. So that's called the Zn group. So it's basically a collection of A, A1, A to the power 2x square and up to n minus 1. Okay. Now, one important thing, let's say we consider Z2 here. Z2 में कितना elements हैं? And what is the multiplication table here? Let us see E, A, E, A. E times E. A times E is E, sorry, A, and A square by this definition will be. Now let us look at these two tables. This is the table for Sn under this binary operation. Here the binary operation is, for example, let's say dot. We did not really specify the binary operation here, which has been assumed. Let us say that is a multiplication, sort of multiplication. Now look at these two tables. Do you have a similarity? See, if we identify F1 as E here and F2 as A here, we see that these two multiplication table exactly matches. So the origin is, this is S2. The origin is very different, S2 and Zn. Okay, these matches for actually for the case n equal to 2, not it will not match for 3. But the beautiful thing is that the origin is very different, but you see the multiplication table actually exactly matches. And there it's the motivation that, okay, I have a group here, I have different group here. Can you do a connection between these two? So connection is, so in general in set, what we have, we can assign one F1 to E here, F2 to A here. But at the same time, in the group, what we have is the structure itself. We have a multiplication table of this type, okay, where we have to satisfy all these properties. Then simple mapping from one element to another element is not sufficient to preserve the group structure. So let us say I have a group G. Let us say I have a group G whose binary operation is multiplication, and let us say I have another group H whose binary operation is, let's say, this cross multiplication. here. Okay. So only defining a function from G to H is not sufficient in order to like compare these two group, or let's say having same properties or something like that. If you want to say, just a simple function will not do the job. Okay. This function also has to preserve some kind of structure. Okay, then only we can say something. I mean, we can compare these two groups basically. Okay. So that is so this structure preserving map is in group, and it preserves the structure. So not only assign F1 to E, F2 to A, it also preserves the multiplication structure that is inherent in the group. Okay? So this structure preserving map is actually very important in the preserving map. So what is the condition I have to have? I have to have that f of G1 times G2. So if we multiply G1 and G2 first, and then take its image into A, and if we take first the image of G1 and then under this multiplication another image and multiply, they should be the same. Then only we can say that this is a structure preserving map. That means the multiplication table for this group G and H will be the same. Okay. So this is called the homomorphism of the groups. This is called homomorphism. Okay. So only one catch is here. Here it's a bijection. F1 I can map F1 to E, F2 to A. Okay, so this is one-to-one as well as on-to mapping. But in order to have a bijection, if we satisfy only this condition, it may not always be a bijection. It may be like structure preserving, but the structure may shrink. That means if we have, let's say, bigger table here, and we can have a smaller table, but let's say the structure is shrinked to a different structure that will come to in the next day. So we'll start from the next day. We'll start from this homomorphism property of a group, not a property, homomorphism of a group. So which is basically a structure preserving map from one group to another. Any questions? Done?